Okay, we're starting the chapter on sorting and searching. So what we're going to be covering in this chapter, we're going to cover sequential searching, two forms of that, and we're going to cover binary searching, which is more efficient. Then we're going to look at hashing, which is a search technique, and we're going to implement also selection, bubble, merge, quick, and insertion and shell sort. So we're going to cover quite a few ways of sorting data. And along with the hashing technique, we're going to look at a map abstract data type, which is similar to dictionary in Python. And we're going to look at how you would implement that. So in searching, usually when we want to search, we're searching for a particular item in a large collection of items. So you can think about searching in a list. Um, Now, when you want to write a searching method, there's two forms of the method might take. You might want to just search and find if it's in the collection, if it's true or false. So you want to check if, for example, the number 5 is in this collection of numbers and return true or false. You also might want to write a way that you can search a collection of things and return the position of where it is. So if it's in something like a list, you could return the index number of where it is. So now in Python, it has a built-in in operator, which does search and returns true or false. So this shows you that. But we're going to be looking at how you implement it yourself. So the simplest search you can do, and this is usually covered in any beginning programming class in the arrays chapter, is to look at sequential search. So sequential search is basically what it means. You sequentially look at every element in the collection until you either find the element you're looking for or you get to the end of the collection and you haven't found it. And then you return true if you succeeded and false if you didn't. The code in the book is a little bit more complex than this. I've simplified it. The author of the book is what's called a strong structural programmer. And in structural programming, you never try to return from the middle of a loop or from a method. But it's perfectly okay to do this. It's just a slight breaking of what's called structural programming, which is a philosophy. So by doing that, instead of having flags to keep track of everything, once I discover a match, I can directly return from the method the result of true. So here's the code. It's the method is called sequential search or function. You give it a list and an item you're looking for. It starts out by pointing to 0, so it's going to look at the first item, and then while the element you're pointing to is less than the length of the list, you compare that element with the item. If it's a match, you return true. Then you increment to the next item if you didn't find it and continue the loop until you reach the end of the loop. If you reach the end of the loop, you get to this return, which will return false. Now, this type of search, we have to first, how do you measure how long it takes? And since the code's going to vary a lot between searches, one thing that is constant is you're always going to be doing comparisons to eventually find the item you want. So traditionally in computer science, we count the number of comparisons as a good thing to measure to determine what big O performance we have. We assume that the list is random, so the original data we assume it's random, and that implies that the probability of any item being the one we want is equal. They all have equal probability of being the one we want. So when we look at a random list and we're searching for some arbitrary data, it could be anywhere in the list equally. So now let's look at actual cases. So when you're looking at analyzing the performance, it's good to consider all the cases. So there's a best case, a average case, and a worst case. So number one, the best case is if the search item is a match at position 0, because that's the first one we look at. Now if that was always true, we would have it would be constant time. We would always find it in the first position. But that's just the best case. The worst case is that we don't find the item at all after we've searched all the items in the list. So that takes n comparisons to reach that point. So the worst case is that we have to do n steps. And when you look at the code, it's just a simple loop that goes from the beginning to end. So you can kind of get a clue that it's O of n. The average case is you're going to find the solution halfway through the list. In other words, if all the items have equal and you average how long it takes, it's going to go range from the first item to the last item, so the average will be half of that. So 1/2 of n. So we have a table that signifies all this. Now, of course, if the item is missing, you're always going to go to the end of the list. So first, if the item is present, you have the best case, the worst case, and the average case. If the item is missing, you always go to the end of the list to discover that. Now, it turns out if you have an ordered list, you can do better. And you can do better in this last line here. So we're going to show you that. So we've changed the code slightly. First, we're going to assume that the list we pass to our method is already sorted from lowest to highest. So here we have the same numbers we had in the other list, but they're all organized from lowest to highest. So if you pick some number like 13, you notice there's a point in the list where all the numbers are more than 13. So you know when you get to 26, there's not going to be any 13s to the right of that. So the idea here is you start a normal sequential search, and if you don't find 13 by the time the number gets bigger than 13, you know you can quit early. You don't have to reach the end of the list. So to do that, we have added just an extra test to the original code. Otherwise, it's the same as the original. That if the item you're at is greater than an item, after you find it wasn't a match, you return false. So that means you reach, for example, this 26, and you're searching for 13. There's no reason to continue searching. So that changes this slightly. Everything's the same here, except the oops, this is a problem. This should be n. So except if the item is missing, the average case, if it's missing, is n over 2. Oh, and the best case is 1, because it could be that the item you're searching for is less than the first item in the list. So that was correct. Now, when we have a sorted list, it turns out we can do a lot better than that. And the idea is that if you have an ordered list, like this slide here, you can find the midpoint. And when you find the midpoint, you can see, well, does the item I have match this midpoint? If it doesn't, if it's greater than the midpoint, you know you only need to look at the right-hand side of the list. So you've made a smaller problem. Now you're just looking for an item in this list. If the item you're looking for is less than the midpoint, you can make a smaller problem by looking at the left side of the list here. So every time that you do a comparison, you can now divide the problem into exactly half the size that it was originally. So that's what this slide is going to talk about. If the item is equal to the midpoint, we've found it, we can return. If the item is less than the midpoint, we now need to search the lower half of the original list. And if the item is greater than the midpoint, we now need to search the upper half of the original list. So let's look at the code to do this. Now again, I've simplified the code, and I don't use any Boolean flags like the author does. And I do that by returning true as soon as I detect that I've found the item. Okay, so let's look at the code. We have binary search. We give it a sorted list and an item. We set first to indicate the first element of the list, index, and last indicate the last element. So first is going to point to the first thing of the part of the list we're looking in, and last will point to the last item. So it starts out pointing to the whole list. And then while first is less than or equal to last, so first and last are equal to each other, that means we've exhausted the search, and we exit this loop and we say we can't find it. Otherwise, what we do is we calculate a midpoint by taking first plus last and dividing it by 2. That's an integer divide, so you always get a whole number. And in this case, it's going to choose 4 as the midpoint for mid. And then we check, is that midpoint what we found? And if it is, we return true. Else, we have two conditions. We have where the item is less than the midpoint and where the item is more than the midpoint. So if it's less than the midpoint, we reset last, which is pointing to the end of the list. Instead of being here, where it was, we're going to reset it to 1 less than the midpoint. So now we have a new list that goes from first to last. If the midpoint is greater than if the item is greater than the midpoint, then we change first. So last is still pointing to here at 8, but first is going to be set to point to 5. So now we're only searching these 4 items. So every time you go into one of these if-else here, you're halving the list. And eventually these will equal each other, and you will have the case, you'll have this case where one of these will decrease below the other, and this will become false, and you return false here.